Right. So we are going to start our, if we talk in terms of book, this book, by Professor Jim Cross and Keith Ross, being shown here, 7th edition or 6th edition, in both editions. We are going to start our chapter 2, the application layer. Okay. There was a question during the break that I should upload the book. I couldn't find the PDF of this book, which is shown right here, 7th edition. Okay. But the PDF of 6th edition, this is the 7th edition. The PDF of 6th edition is available on just one click. Okay. You Google it and you will, most of you have it, right? Okay. I think 7th, you should have the PDF of 7th edition as well. Okay. Okay. You have uploaded it. That copy is also pirated. Okay. Okay. I am being handed over the hard copy of this book, but it's a good one, right? 7th edition, right? Okay. The difference between the 6th and 7th edition, there is no difference in the first 3 chapters. Okay. Until the transport layer, the introduction, the application layer, and the transport layer, they're the same. So if you have 6th, it's fine right now. But when we move to the network layer, then there will be a little portion of the difference is not huge. But in the 7th edition, Cross and Ross, they have added the portion of software-defined networking. So they have divided the chapter 4 of 6th edition into chapter 4 and 5 in 7th edition, in 2 chapters. The control plane of network layer and the data plane of network layer, two separate things. Okay, we will right now remain to the task in hand, and we are going to start chapter 2, application layer. And this is the whole outline, but obviously, as I have told you guys repeatedly, that I am just trying to bring everyone on the same networking base. So this is not the outline that we are going to cover. We will just cover the DNS 2.4, topic 2.4 over here, and maybe we will touch a little bit HTTP. Okay, not the basics of HTTP you should know, but in terms of networking, we will discuss the ways of reducing PLT, page load time. Okay, that is something which is not part of the Cross and Ross book. This is something which I will use my own set of slides for that. Okay, but the methods to reduce page load time, those are some important methods. Okay. Okay. So obviously, not all, the whole content which is shown right here in the slide. Okay. But this is the goal of general goal of having an understanding of the application layer. Okay. And the general goal is that we have a conceptual implementation aspects of the network application protocols. Okay. So we should have an understanding of the transport layer service models, which means that this is one slide. This slide I would like to discuss. Okay, because this slide is related to the core of the networking concept. So I mean, on the basis of what a particular application decide which transport layer service model I'm going to use. Okay, so basically we have 2 transport layer service models. We have a model of TCP. Okay, that's a separate service model. TCP service model, if you put in words, it's reliable byte stream. The service model of TCP is a reliable byte stream, and the service model of UDP is unreliable messages. Okay, these are 2 separate service models. Okay, TCP has a full set of service. UDP has a bare minimum service. Okay, so some applications tend to prefer TCP, and some applications will prefer UDP. Okay, so we will discuss in just one slide before going to DNS that which particular service model an application prefer. Then there are one slide each on client server paradigm and peer-to-peer paradigm, but I should you all know that applications are divided in two paradigms: client server and peer-to-peer. So we can skip that. Okay, and then CDNs. We will study CDN. CDN is a very interesting topic and a very cutting edge, state of the art topic. So we'll study CDN, but we will study CDN in the context of HTTP, not in the way in chapter 2 Cross and Rods had discussed. It's a very simple discussion of CDNs. We will go in a little bit detail of CDNs by discussing by discussing CDN as a way to reduce PLT. How CDN's content distribution network can be used to reduce PLT, page load time. I mean, how CDNs can be used to load the pages more quickly, to make the user experience of internet much better. Okay, so we will study CDN as a method to reduce PLT. Okay, and then obviously we will study a little bit of HTTP and DNS over here. Okay, and DNS we are going to start right now in a couple of slides. So let's have a look at one or two sites. These are very basics. I'm not going to touch these basic things. Okay, then we have two possible structures of application: client server and peer-to-peer. Let's just discuss their difference. Okay, so name one application which follows the client server paradigm. Facebook is the name of a website provider. It's not an application. In terms of networking, the application is HTTP. Okay. Facebook and Cricinfo and CNN and Twitter, these are not applications, not internet applications. These are not internet applications. The applications are HTTP. Okay, hypertext transfer protocol. So web service. Okay, application is FTP, file transfer protocol. So file transfer service. SMTP, simple mail transfer. So email service. Okay, these are the applications. An application name of application is another name is Skype. Okay, Skype is the name of a separate application. Okay, so for instance, HTTP client server paradigm, FTP, SMTP client server paradigm, and Skype. Okay, torrent. These are peer-to-peer. Okay, what are the benefits or losses? You all know client server. We have a server as an always-on machine, permanent IP address, and these days servers are no longer standalone servers, single devices. These days, the number of users, the internet user over the globe are so much that we need data centers. Okay, to scale the servers. Okay, so the popular websites are not served by one single machine, by one big server, but they are mostly served by the data centers these days. Okay, and the clients they communicate with the servers. They are the one who are receiving the content, and they may be intermittently connected, so they come and go. We connect on our ease, right? We are not an always-on machine. Okay, when we want to use internet, we connect to internet and so on. We may have dynamic IP address because we keep changing our IP address. No one will contact us like the server. The server has a permanent IP address. Okay, and they do not communicate directly with each other. In this model, in peer-to-peer they will, but in this model they communicate to the server. They get their content from the server. The peer-to-peer model, the biggest advantage of the peer-to-peer model compared to the client-server model is this, written in the red font: self-scalability. So each added client in a client-server paradigm is a burden on the server. Each added client. You know, we get one more client, it's a burden on the server. We get one more client, it's a burden on the server. After some number of clients, we need another server. After some more number of clients, we need a third server. Okay, but the beauty of the peer-to-peer architecture is that it's self-scalable. With self-scalability, it means that each new peer will bring its own resources to the system. So it will be a burden to the system, but it will, or at least it should, in principle, bring its own resources. Okay, although it's a challenge. It's a challenge because all of us, when we use peer-to-peer service, we want to be leechers, not seeders. These are the two terms used in P2P. Okay, seeder is the one who is providing the content, and leecher is the one who is obtaining the content. And we all want to get the content, get the movie, get the file, not provide the content. So this is one of the challenge of P2P services. Okay, so now they have sophisticated protocols for this. Torrent used to do something like that. That when you are seeding a content, they start leeching the content from you from the backend, or they have some set of incentives or things like that. Let's don't go into the detail of the torrent, of the way torrent works, but I mean, three challenges. One of them, another one is security, and the third one is the asymmetric distribution of bandwidth. So the DSL we have studied in chapter 1, the DSL has asymmetric distribution of bandwidth. So less for uplink and more for downlink. The DSL is designed, the bandwidth distribution of DSL is designed to facilitate client server paradigm. Okay, the bandwidth distribution of DSL, ADSL. So basically the access networks, the access technologies that we are using, the bandwidth distribution of access technologies is designed to facilitate client server paradigm, because that is the old one. It is there since 80s. Okay, so the telecom companies, the operators, when they started providing the ADSL services or other broadband services, what they did, they had a lower portion for uplink, because the request is few bytes, but in response the whole page, the whole movie, the whole book, the whole content is going to be downloaded, and more portion for downlink. But this challenge for P2P. For P2P, you need equal bandwidth for uplink because you are seeding the content, and equal bandwidth for downlink because you are leaching the content. Okay, so three challenges are there for the P2P architecture. The applications of P2P architecture: security, incentive, and asymmetric distribution of bandwidth. These are the three challenges. Okay, but they are dealing with it. P2P is very, very common these days. Okay, it's a very, very common architecture. So they are dealing with these three challenges. Even broadband services are now giving you either a flexibility in the bandwidth distribution or equal bandwidth distribution. You had a raise of hand. Yes. Skype is a peer-to-peer service. Yes. Okay. Even every peer-to-peer architecture has their own servers to authenticate the users. So if me and you are going to have a Skype conversation, first that call is going to be authenticated and routed through the Skype, one of the Skype server. But after that, the whole communication session will be between the peers. So the server is there only for the bare minimum purpose. Okay, but there are Skype servers. I don't know the architecture of Teams. But if you are not recording the call, it is Skype has a whole plethora of calls which are very, very highly informal between friends or family and things like that, which are not going to be recorded. So in that case, Skype has a business model as well. So Skype is there for normal users, and Skype is there for business as well. So the basic, basic version of Skype, or the way Skype started was a peer-to-peer way, and the servers were only there to authenticate the user and to facilitate their connection, their calls. And after that, the server has no role to play. Okay, but these days, yes, you're so right. We have the call recording option. We have many other things. So it may be possible that the server has more role to play, and the calls are being routed through the servers. Okay, right now let's move. We know I just discussed that that the transport layer, the core functionality is to provide process-to-process communication, and for that functionality, the transport layer use port numbers to address the processes. And in terms of operating system, the operating system create a separate socket for each process running on it, and a socket comprises of two addresses, and a socket is something like that. Okay, a socket is a boundary between application layer and transport layer. Below that boundary, you and me as an application developer, if we are going to develop a new application for internet, below that boundary, the only control we have is the choice of transport layer protocol, nothing else. Everything else is being governed by the operating system. Okay, you see here, controlled by the operating system. This is controlled by the app developer. Okay, you're getting my point. The upper portion, you are going to write. Let's hope that any one of you is going to write the next killer application of the internet. Okay, what you are going to do is you are going to write an API, application programming interface, over here. You will use a certain port number to associate it with a certain known protocol: HTTP 80, SMTP 25, FTP 21, 22, DNS 53, things like that. They all have dedicated port number. Okay, or if you don't need any particular known protocol, you have your own. You are going to write for your own application a new set of protocol you will either have a new dedicated port number or some ephemeral port number. That's not important. The thing is, what you're going to write over here, you have every control over here, all control. Whatever you are coding is going to be a part of your application, but below that boundary, below the socket, okay, and the socket will be the door with which you are going to your process is going to be identified by the operating system, and you are going to push your messages down there, and you're going to receive your messages from up there. Okay, so this is like a door. Okay, जिससे बाहर आप अपने messages भेजें, and there's a postman over there. There are more than one postman over there, and the only decision, the only authority you have is to decide which postman you are going to give your message to. And both postmen have their own service model. One say I am a reliable byte stream, and the other say I am a unreliable message, TCP and UDP. So below that boundary, you only control you have is the transport layer protocol you are going to use. Okay, so socket address is basically based on two things. A socket is identified with the help of IP address and port number both. Okay, so IP address is the destination IP address, and the port number is the destination port number. So the process at the destination end which you are going to address. Okay, so this makes your socket. If you are not getting the idea, don't worry about it. It's the concept is something like that. It is an identifier in operating system which each operating system used to identify each and every process. When you're using internet, you're downloading a file, you are having a Skype call as well, you are browsing the internet, you are doing multiple things, right? Behind all these things, there are separate operating system processes, and all these operating system processes are being identified by their socket addresses, and the socket address is built up with the help of IP plus port number. So for instance, if you are doing cnn.com plus the Skype call plus a file transfer, file download from a server, so one socket will be having a destination IP address of cnn.com and the port number of 80 because it's HTTP, right? Another socket will have the destination IP address of that file server, wherever it is, whatever the address is, and the port number of 21 because FTP is on port 21. Okay, that's the socket address. So that is how operating system identify your different processes, and you as a user, we do that all the time, right? We have multiple processes running over our devices. Okay, so this is just an identifier for the operating system. Okay, right. The thing that I want to highlight before going to DNS is I started with this question that applications need to decide which transport layer protocol they are going to use. Okay, and before deciding, so for instance, you have a message, you have a letter, and there are two postmen outside the door, and you want to decide which postman to give that letter to. You want to understand the importance of the letter. Okay, so if the letter is important, you will give it to a reliable postman. If the letter is not that important, you may give it to the unreliable postman who is slightly faster than the reliable postman. There is different service model. Okay, talking in terms of networking, the point I'm trying to make is that which transport layer protocol to use before going into that. The thing is that applications require different transport services. So which transport service does an app need? This is a more important question to answer. And applications generally tend to require either some or all of these four services. Application require data integrity. Some applications, they say that for me, it is very important that whatever I transmit should be received as it is by my receiver. Okay, data integrity, file transfer protocol, SMTP, simple mail transfer protocol. For these applications, data integrity is very important. 100% reliable transfer is required. Okay, some applications, other applications, for example, audio or video services. For instance, if you are watching a live match and if there's some packets are being lost, do you think that video streaming service should recover that lost packet? I mean, if some packets are being lost in the live match and you recover those packets, it will be just a distortion, a noise in the next transmission. And for the user in the live match, those lost packet will like a distorted screen or like a glitch. So be it. It's okay. A lost Skype, a lost packet in a Skype conversation is like a glitch being heard in your voice, or a little noise or jumbled up thing, right? You don't want to recover that packet because it will, interfere in the next conversation being going on. But a lost packet in an email should be recovered, must be recovered, so that the content is going to be reliably transmitted and received at the internet. Okay. Usually, the interactive applications, they are loss tolerant. If something got lost, so be it. Don't recover it. And usually the other applications which are not interactive in nature, they are not loss tolerant. Okay, but they are delay or throughput tolerant. Okay, so if you receive an email with a delay of 5 seconds, I mean, it's okay. You want to have that email, right? Okay, you want to have that file. But if there is a 5-second delay in an e-gaming session, you are going to, throw your laptop away, or you are going to do something, because the other party punches you and you receive that punch after 5 seconds. What's the point of playing? Understand? Okay, so some applications require data integrity, some applications require timing, and some applications require throughput and security. Okay, you got an idea. Okay, usually these two things are coupled together. The applications who require data integrity, they tend to require security, and usually these two things are coupled together. The applications who are delay sensitive are also throughput sensitive. I mean, they require more throughput and less delay because they are interactive in nature, like games, like video streaming, like audio calls, live calls, Skypes, VoIP, things like that. Okay. What services are available? Now let's have a look, because application has to decide that I have to throw my message below that boundary, below socket, and I have different protocols available. They all have different set of services. So what services are available? There you go. We have two different service models. It's actually, there is a huge dichotomy at transport layer. You have a protocol at transport layer who offer you a full set of service, okay, who offer you reliable transport, flow control, congestion control. And there is a protocol at another protocol at transport layer who offer you bare minimum services, who says that give me your message, I'll just do the process to process communication and nothing else. And but I'll try to make sure that I blast away as fast as possible, because I do no congestion control, no flow control, and I don't care about the network. I'll just keep sending your stream, keep bombarding the network with all the packets. So audio, video streaming, e-gaming would like to have UDP service, but the SMTP, FTP, they would like to have TCP service. But a funny thing is that no service model, neither UDP nor TCP, provide you any guarantee of timing or throughput. These two services are guarantee is not provided by anyone. UDP will try to blast away as fast as possible because UDP do not provide congestion control, but there is no guarantee. Okay, and why there is no guarantee? No transport layer protocol. If there is a new transport layer protocol, no, that will not provide you any guarantee in delay and throughput, because internet is a packet switch network. In a packet switch network, no one can guarantee delay or throughput. No one. Okay, you can only guarantee delay and throughput in circuit switch network. Okay, you can try to do that. You can. We studied in statistical multiplexing. We want to have a circuit-like behavior. Okay, but guarantee is a huge word. Okay, no one can guarantee you this thing. Okay, and another funny thing is even security is not provided there in the basic version of TCP, but TCP enhanced with SSL or TLS will provide you security. So the service model is something like that. TCP does not provide timing, minimum throughput, guarantee, security. UDP does not provide anything. UDP does not provide reliability, flow control, congestion control, timing, throughput, guarantee, security, connection setup, or anything else. Okay. Basically, UDP does what? It take the message, it attaches the port numbers, and it give it to IP. That's it. Okay. But we'll see. A question arises in mind. Then why is there a UDP? It's still very useful, and it is not only being favored by the applications who are interactive and video, audio, and e-gaming. It is being used by some important applications as well. Okay, UDP is being used by DNS. UDP is used by SNMP, Simple Network Management Protocol, and UDP is used by DHCP, Dynamic Host Configuration Protocol. When you turn on your machine, you get a dynamic assignment of IP and your gateway. Okay, and this is being done by the DHCP, and the DHCP run over UDP. Okay, and DNS, a very important protocol. DNS run over UDP. Okay, so these are some of the important services which UDP uses. And SNMP, for instance, I will not be able to start UDP, but this is very important discussion. I am having a look at the clock, so let's have some more in-depth discussion on what we are discussing right now. I will start DNS tomorrow because there is no point in starting it right now. Why bother? Why is there UDP? I was answering this question, okay, and there is a plethora of terms on this slide which still yet to be discussed. So let's remain on this slide, okay. So why bother? First, let's go to the right half of the slide, which is shown over here. The UDP service model, unreliable messages. Okay, unreliable data transfer between sending and receiving process. So for instance, the next application that we are going to discuss tomorrow, DNS. Why do you guys think DNS uses UDP? Answer should be very simple. In the DL mode, you can turn on your mic and speak. Why DNS uses UDP? DNS is an important application, right? DNS does what? IP to host name translation, host name to IP translation, sorry. Host name to IP, right? To reduce page loading time. Okay, yeah, everything boils down to that. It's a safe answer. Yes, okay. DNS is a sort of application. DNS is a sort of application layer protocol which is not invoked by the user itself, but rather, listen carefully, rather DNS is being invoked by the application which the user invoke. The user invoke HTTP. I want to have a look at some website. User invoke SMTP. I want to check my email. The user invoke FTP. I want to transfer this file. But that FTP or SMTP or HTTP at the back end, without user being without the knowledge of user, invoke DNS. Okay, so DNS is an application layer protocol which is not invoked by the user, but rather it is invoked by the application which is invoked by the user. Now, if every application layer protocol, HTTP, SMTP, FTP, and others are dependent on DNS, DNS must be fast, because any delay in DNS will add in the delay of all those applications, right? TCP does what? If you want to query a host name to IP translation, and your machine and the DNS server, they work on TCP, then first you will do something like that. Hello, how are you? You say, hello, I'm fine. Okay, so this is the host name. What is the IP address? And this is the IP address. Okay, thank you. Bye bye. Thank you. Bye bye. So there are 5 to 7 extra messages because TCP is connection oriented. TCP will first build connection, then talk. Okay, it's like अस्सलाम वालेकुम, क्या हाल है? ठीक है जी. Then अपनी बात की, टाइम क्या हो रहा है? और फिर जवाब लिया, अल्लाह हाफिज जी, अल्लाह हाफिज जी. Okay, so proper connection management, proper connection termination, right? And this require extra headaches. Now you guys must have noticed that when you access a website, in the address bar below, and I've talked about this in the previous week as well, that with the advent of CDNs, the content is distributed, and when you load a single page, you tend to get different content of the page from different servers. So for all those things, for all those servers, there will be separate DNS queries. So if you are getting so if a web page is made up of 100 images, 100, let's say 100 web objects, and these web objects are scattered over different servers, let's say 10 servers, you are going to have 10 DNS queries. The purpose of whole story is to make you understand the fact that if DNS is slow, your whole user experience will be slow. The PLT will be more. Okay, so if DNS has to be fast. Now the thing is that DNS is unreliable. So what happens is, if every now and then, I mean, if 1 out of 100 messages got dropped and don't receive, you can have another DNS query, but it is not a wise way to a wise thing to use UDP, so to use DNS with TCP, because that means that for 10 queries you will be exchanging 70 messages, while on the other hand, for 10 queries you will be exchanging 20 messages. DNS request, DNS reply, DNS request, DNS reply. UDP does nothing. Okay, so DNS uses UDP. Okay, another example is SNMP, Simple Network Management Protocol. This protocol is invoked when the network is in dire state. Now imagine कहीं पे आग लगी हुई है, right? There is a fire at some place and you say, "Assalamu alaikum, क्या हाल है, ठीक है? या आग लगी है वहाँ पे यार, बुझा दें जाके." If there is fire, if there is a problem at any place, what you will do is that you will immediately send your message. So you will not do a TCP-like transmission, you will do a UDP type. The UDP is being used by important applications as well. So it's not like that you don't need this service, you need this service. On the other hand, as I said, there is a perfect dichotomy. You have TCP who does reliable transport, okay, who makes sure that the best effort service of IP, if the packet is lost, corrupted, duplicated, or out of order delivered, it has to be corrected, all these things, all these problems. And then the TCP service also does flow control, which means the sender won't overwhelm receiver. Okay, so the sender will not send too much too fast so that the receiver cannot handle it. And it also does congestion control, so that the both are controlling the rate of sender. Flow control is controlling the rate of sender for the well-being of receiver, and congestion control is controlling the rate of sender for the well-being of network. Okay, one is controlling the rate of sender so that the receiver do not get overwhelmed, and the other one is controlling the rate of sender so that the network do not get overwhelmed. Okay, and this congestion control is very, very important. Okay, and then connection oriented setup, which means connection is going to be set up and it will be tiered down properly. Okay, so this is the service that TCP provide, and this is the service that UDP provide. Application have to decide out of which service model they want to use, and based on their usage like this, they tend to prefer one over the other. So for instance, in this table you can see that file transfer, it is data loss, no loss is tolerable. Throughput, it's elastic, no problem. And time sensitive, not that time sensitive. Email and web documents are the same, but real time audio video, it is loss tolerant. It can tolerate some losses, but it desired a certain level of throughput. It desired a certain level of time sensitivity. And similarly, audio video, if it is in the stored form like YouTube or interactive games or text messages, all these things are falls in the second category, which needs delay or throughput compared to data integrity and security. Okay, so we conclude here, and I'm going to stop the recording. I feel a bit guilty because I should have started DNS, but we'll conclude DNS tomorrow. We'll start and conclude tomorrow. No worries. It's a one lecture topic. But I hope